Thank you. Everybody, so I'm super psyched to be here. It's been a really fun week. I've had lots of interesting conversations with you, and I look forward to you guys yelling at me at various things I say now. So yeah, I'm going to talk about time and learning in a dynamic world. And so a little executive summary of what we're going to talk about over the next hour or so is here. I'm going to introduce you what I think of what learning is as a neuroscientist and how we got there. But then I'm going to put on like my other hat as someone who studies artificial intelligence to talk about how we model learning and then what's wrong with our models based on how it's not really aligned well with what's biological learning. And then a proposal for how we can make it a little bit closer. So I want to start with this video. And as was just mentioned, there's lots of different scales here. So this is going to be a video of a single-cell organism. Learning in single-cell organisms doesn't happen within a lifetime. It happens across lifetimes along evolutionary timescales. So spatial scale, small. Temporal scale, big, like think millions of years. And what it learned to do is this crazy behavior where it hunts. And so what you can see, did you guys see it? That little guy shot a harpoon, this one shot a harpoon at this one, and then drags it away. Okay? Now, I don't know if any of you have ever hunted, but it's not that easy for us. Like especially if we don't have harpoons, like I don't have one in my body. But this one, over evolutionary timescales, learned how to hunt, which is a very complicated activity where you have to find the thing, shoot the thing, at the thing, pull it away, and then absorb the thing. So it's a pretty cool example, I think, of learning. I don't know if anyone has seen this video, but this is a video of squirrels learning. And so this guy set up a little Ninja Warrior course for squirrels that starts here and has to get all the way over to these nuts where there's food. And you can watch the video, it's like 20 minutes, it's pretty entertaining. And what you see is that each little station, squirrels fail a bunch of times, and then eventually one of them gets it. And what I think is particularly interesting about this video is it shows multiple kinds of learning. So one kind of learning is through trial and error, each squirrel will learn something. Also, some of the squirrels learn simply by watching the other squirrels, something called imitation learning. So there's multiple different things called learning happening at this scale, which is obviously very different than the kind of learning that happened for the single-cell amoeba. Okay, so that's squirrels. And now I want to show you a video of humans. So this is a bike. And a person riding a bike. Probably many of you know how to ride a bike. But what they did on this bike is they switched the handlebars. So when you rotate to the left, the wheel goes to the right. And when you rotate to the right, the wheel goes to the left. Okay, now these people have already learned how to ride a bike. Now they're going to try to ride this flip handlebar bike. And you see how like catastrophically they fail. And this dude like goes around the country, or maybe the world, showing people how stupid they look because they think they can do it, but within like 1 second they fall. It turns out you can learn how to do this. It takes, if you already know how to ride a bike, it takes weeks and weeks. And once you've learned, now you can't ride a normal bike anymore. And then you can practice more and you can learn how to ride both ones. So there's different kinds of learning. This would be called something like reversal learning. And the point is it happens for humans, it happens for squirrels, it happens for single-cell amoebas. It's a ubiquitous property in the animal kingdom. Okay, so what's the deal with biological learning? My claim, and it's not mine, lots of people say this, learning is the ability to use the past to improve future performance. It's pretty simple, straightforward, vernacular definition. The claim is it evolved because the past is related to the future in certain ways such that that's useful. Right? If the future was arbitrarily different from the past, learning would be nonsense. You couldn't do it at all, or you could, but it wouldn't be helpful. The point is the reason it evolved in many different scales, in many different organisms, many different mechanisms, is because it's so useful, because the future is like the past in certain ways. Okay, that's actual learning, what animals are doing. But now I want to switch gears and talk about how we model learning. So it's been at least 100 years of people trying to model learning in various ways. And in AI, anything we call learning is a model of it. There's an actual biological phenomenon, which we've all observed and experienced, that's learning. And then there's our formal models of it. And they're distinct things, and for the purposes of this talk, it's important to distinguish those two. Now, over the last 100 years or so, people have defined multiple different formal notions of learning. There's something called probably approximately correct learning, basically the workhorse of all of AI right now. There's reinforcement learning and online learning and two different things. I'll get to a little bit. But I want to point out this famous quote from George Box, famous in the sense that like 20 statisticians know of it, but we like to think it's famous. And what it is all models are wrong, but some are useful. I like that quote. I'm not sure. Anyway, it's a fine quote. So let's look at this model of learning. This is a model of learning that was developed in the 30s by a couple of Italian guys named Glavenco and Cantelli. So if you've heard of machine learning, artificial intelligence, a lot of it is based on the work by Vapnik. If you read Vapnik's first paper on the topic, he cites this article. In fact, theorem 1 in his first paper is theorem 1 in this paper, and he gives them credit. So it's like there's a continual line of intellectual development starting in the 30s by these two papers. And they're in Italian. My Italian's not great, but I know risulta probably means result. And here's what the result is. And so let me just unpack the equation a little bit. F of x, that's the distribution of x. And this f, I think that's an h of x. That's the empirical estimate using h samples from x. The difference between these two, using some norm that's defined, is less than epsilon. So this theorem is stating if you have enough data, you can estimate any distribution arbitrarily well. That's the result from the 30s. These were probabilists. They didn't say learning then because they weren't trying to convince people that it was related to intelligence. They just said estimation. It was another like 20 years or so before people said learning. They just said estimation, and that meant you can estimate this distribution. No matter what the distribution is, as long as you have enough data, it can get arbitrarily close. Okay, so Vapnik comes around, and Valiant comes around, and a bunch of other people, and they talk about something called probably approximately correct, and it's essentially what I just said. It's the workhorse of modern AI. So almost all of the developments from 2012 forward are leveraging this. They're leveraging algorithms where the theory suggests that they will work because of this thing. So it's very useful. However, it's also very wrong. And it's wrong in two particular ways. The first way is that it assumes that data are IID, which means independent and identically distributed. In other words, the distribution of the data in the past and the distribution of the data in the future are exactly the same. Obviously, that's not true in the real world for many things, maybe all things, right? Things are changing in time. Another thing they assumed is that the goal was fixed. That's also not true. I mean, we just think about like throughout our lives, when I was a baby, I really wanted like breast milk and someone to wipe my butt. I don't want either of those things now. And later in my life, maybe I want them again. But the goal has changed, is the point. Okay, so why might you care? Well, here's one of my favorite examples of a catastrophic failure of AI. It's very important to know how many people will get the flu where, because ICUs depend on knowing that, because you can basically, the hospitals in the US are designed such that the ICU capacity is built around how many people in that locale will get the flu during high flu season. Because if there's more than that, then those people will die because they need an ICU. So it's an extremely important social problem. And the CDC uses basically the dumbest possible way to estimate how much flu there'll be, say, next week. They look at how much flu there was last week, and they say about the same. It needs almost no data and no machine learning. Now take Google. Google has essentially all the data in the world and all the computers in the world and a bunch of really smart people. And they said, we'll just build an AI thing that will do better than the CDC. So they trained it on a bunch of data up till 2011. And it seemed like it was working pretty good. And then they deployed it later. And what you can see is when they deployed it, this orange line is Google, the x-axis is time, the y-axis is error, and it goes, this is 0 and this is 150%. Once they start deploying it, it's almost always bias positive. Not only that, its errors are huge, like 150%, way bigger than the dumbest possible thing. So this is, biggest computers in the world, most data in the world, smartest people in the world, utter failure. And I argue one of the main reasons for that happened is because they failed to incorporate time. things are in fact changing in time. And if you don't deal with that, then you get huge embarrassing failures like this.
So, Josh, I mean, if you go back to where you started with, I mean, so I thought one of the points, I'm not sure how like people saw this earlier in the earlier workshops, but somehow though I thought one of the points of the deep learning revolution was that statistical learning theory is not telling you what actually happens, and you actually you're just using these gradient flows to actually get information. So is it really fair to say that it's statistical learning theory which is kind of running the revolution? I mean, sorry, I don't mean to derail you.
Yeah, no. Okay, so the question is it fair to say statistical learning theory is like running the revolution? And I say, absolutely fair. The reason I say is because if you look at, say, early papers in deep learning, like the progress really depended on people demonstrating that deep learning could do a bunch of things that other statistical approaches were doing, and then them figuring out how to write the code to scale. But they're not like, they're just doing, there's a paper from 1951 by Hodges and Hicks where it's like, that was the thing, and they use basically a perceptron, and now it's off to the running. So I think so. It's similar, like, recent analysis of, say, attention networks and transformers showed that they're basically Nadaria-Watson kernels, which are also ideas from like the 60s. So yeah, I think it's really, it needed that stuff basically to have compelling evidence that it's going to work. Okay, another reason you might care is intelligence is what makes us us, just us as human beings. I mean, it's called Homo sapiens, thinking people. So from my perspective, like the most important thing for us to understand about us, or at least for me to understand about me, is what is going on here? Like, what does it mean to be thinking? And a core property of thinking, I believe, is learning, because we come out not really knowing that much, and then we know a bunch more. So I think it's really fundamental to understanding ourselves as well. So here's this book, published in 2013 by Leslie Valiant. For those of you who don't know who he is, he was one of the founding people involved in the AI revolution. He won the Turing Award, all the awards. So he's very highly respected. And his claim in this book from 10 years ago, probably approximately correct, which is his theory, that has no notion of time, is nature's algorithms for learning and prospering in a complex world. So this big shot in AI is claiming in a book that this is how learning works in the natural world. And what I'm saying is that's totally wrong. I don't know if you'll agree with me, but that's my claim. Okay, so I'm going to just go through and unpack both probably approximately correct learning theory, and then I'm going to interleave it with how we're modifying it to be what I think is more appropriate to describe learning in the natural world. And then later I'll show you how it actually matters empirically. So we start with a data model, and we're going to focus on supervised learning for simplicity. So input is going to be maybe images, could be text, could be tokens. Output could be disease status. I do a lot of biomedical research. It could also be the next token. They come in pairs. Each pair in this pack model, probably approximately correct, is pack. Each pair is IID, meaning identically and independently distributed. And we're going to say D, capital D, is a data corpus, which is just a set of n pairs. It's important that it's a set because sets you can order arbitrarily and it doesn't change anything. Okay, so the first and maybe the biggest change we make is we say that the pairs are neither identical nor independently distributed. Okay, so we don't have n pairs of IID data. We have n pairs of data, and it's going to be in a sequence. Okay? For those of you who have like a bit more background in probability theory, where we change it to the data sample from a random variable to a stochastic process. Okay. Next, there's a hypothesis. So this is a word people have been using in machine learning to describe the function that we're actually learning. So H, the hypothesis, it eats some input and it spits out an output. So it could be H, you give it an image and it tells you whether it has a disease or not. Or you could give it a sentence and it tells you what the next word is. Capital H is a set of all possible H's, and there's many different capital H's that people have studied. Deep nets is one of them, obviously. Random forest is another. Linear functions are another. There's many more. We are modifying that to put time right in here. So what we're going to say is H, it's going to take just some input and a timestamp, like exactly when the input happened. And it's going to output Y for some time. Okay, and so now we can modify all these things to just include time. And it's relatively straightforward how to do it. I'm going to show you how to do it later, but that's the formalism that's being changed. Okay, now no one's giving us the right hypothesis. We need a learner that tries to find the good hypothesis. So a learner is going to eat some data corpus and spits out a hypothesis, just like that. And we want, as I said, to choose a good one. We're going to change this too a little bit, or we're going to say it's going to output a hypothesis sequence. So instead of getting one fixed hypothesis at one time, and this is really key, what we output is an infinite sequence of hypotheses. I'll tell you how to do that in a computationally reasonable fashion. You have a question?
Just a quick one. You said it before. Are we assuming the data, are you associating time to the pairs or not?
Yes. We're going to output an infinite sequence of hypotheses. So it's going to say, for a given x, at time 1, what do you think y would be? At time 2, what would y be? At time infinity, what would y be? So it's going to be essentially forecasting all possible future times. In pack learning and much of machine learning, we try to find the hypothesis that minimizes some notion of loss. And so often we're talking about minimizing the sum of the errors between what it predicts and the truth, or the squared errors or something like that. And we want to find a hypothesis that does that well. Once we have time, what we're talking about is minimizing the loss between predictions and the truth integrated over the entire future. So we added a sum in here integrating over time. And so this is somewhat similar to reinforcement learning, if you know about reinforcement learning, where you care about the sum of future rewards. It's much, much simpler than reinforcement learning in certain ways because I haven't said if there's necessarily control involved or you're changing the environment. It could just be like some inference problem where it's like a normal classifying images that happen to be changing over time. So it's related to reinforcement learning in certain ways, but different in other ways. Okay, so here's a fundamental theorem of pattern recognition. I kind of alluded to it earlier, that paper from the 30s. And it says, a learner exists with the following property. With enough data, it will select a hypothesis that is probably approximately correct. Okay, and this is a slightly more formal definition, but that's the basic idea. What we did in our paper that's coming out next week and on Archive Now, before I say that, there's a bunch of hypothesis classes, learners with this property. Histograms support vector machines, random forest, empirical risk minimization. There's also a bunch that don't have this property. Linear regression does not have it because there's all sorts of functions that it can't learn, anyone that's not linear. Also, deep networks using SGD don't have it. So all the things, it's kind of related to your question, really what we're doing doesn't have the nice theory, which kind of pokes a hole in my earlier argument. So, we can fight about that later. So we generalize this theorem. So we're calling this prospective learning because you have to do prospective thinking about the future. And the theorem that we have is a learner exists with the following property. With enough data, it will select a hypothesis that is probably approximately correct forever in the future. So that's cool. It's a little bit weaker because it's not true for all possible distributions, stochastic processes. There's obviously some stochastic processes, like if it's kind of totally random, you can't do it. So it's a smaller class of stochastic processes. It's not all possible distributions, but it's big and it's helpful. So that's the basic theory. Here, just so you know I'm not like blowing smoke up your ass, this is the actual theorem statement in the paper. You can get it on archive. We're presenting it at NeurIPS in a couple weeks, but there's a bunch of formal stuff and it's real. Okay, so you may be thinking, he said you include time, but how do you include time? Well, it's actually pretty straightforward empirically. Let's just say we have a multi-layer perceptron. Normally it takes some inputs. There's maybe a fully connected layer with some ReLUs, a couple of those, and then another fully connected layer and a softmax for classification. We literally take time, like the absolute time of now. If you're like in the theory of time, just choose whichever version you want. And then we do a time encoding. So we basically project it into a vector. Could be, say, 64 dimensions. You can think of that as taking time and maybe doing a Fourier transform on the actual time value. And so now you get a bunch of dimensions. And we literally just concatenate it to the input and put it in. For a prospective convolutional neural network, we have normal inputs like images, and maybe there's a conv layer and some max pooling, and then a bunch of other stuff. Here, we put in time slightly differently, and it turned out empirically it mattered where to put it. We did a time encoding, added like a little multi-layer perceptron, and then concatenated it after all the convolutional layers. So we basically treat the convolutional layers as feature learning, and then we put it in at the end. And so how do we encode time? Basically took the idea from the early attention models. The original transformer encoded time like this. So this axis is time, and this axis is dimension. And so at any given point, you would embed it like in this vector. We slightly modified it, but the details aren't that interesting, I think. You can think of it as we just did the transformer trick if you want. OK, so here's the most basic result and the simplest, horribly embarrassing failure of, I'd say, existing AI tech and our proposed solution. So the deal is we're going to say there's two tests, task A and task B. Task A is it's gray if it's a positive number and it's black if it's a negative number. Task B is just a sign flip. OK? And now what we're going to say is this x-axis is time. And we're going to say what's happening with the data is every 20 samples is going to switch from task A to task B. We didn't tell the algorithms that. That's just what's happening. OK? So after 20 samples of B, now it switches to A, then it switches back to B, then it switches back to A, reliably every 20 time steps. So here we're going to compare the performance on instantaneous risk, basically the average error, over time on a bunch of different algorithms. Chance is 0.5. Oh, the chance line didn't show up right now, but it's 0.5. And here's a couple algorithms that we're comparing to. So Bayesian gradient descent is like last year there's a publication doing a fancy lifelong continual learning algorithm where it learns that there are multiple tasks and tries to figure out which task you're in and do the appropriate thing. So this is kind of like state of the art. Online SGD is a pretty standard algorithm. You're just doing normal deep learning, but you update the parameters in online fashion rather than in batch. And follow the leader is basically a classic algorithm in online learning theory. What you can see, and then prospective learning is our algorithm, which I'll explain in a bit. Well, you can see the other algorithms all do something really funky, which kind of makes sense. It learns task A, but task A is exactly the opposite of task B. Like if you know task A, you do the worst you can possibly do for task B. Because in task A, you think anything over here is gray. Once it switches to task B, everything in here is black. So what happens is these algorithms get so bad. They figure out which tasks they're in, but then when it switches, at start is the worst possible thing they can do, and they eventually learn, oh, I'm in task B, and they switch back to task, and then it switches to task A, and they're as bad as possible, learning that is task A, et cetera. And they keep switching like this forever. Our algorithm learns after about 250 time steps, samples, what's going on. And the deal is, what it realizes is, it can predict when the task is going to switch, because it's been switching reliably, because I've encoded time and given it time. So it knows at time 40, it's going to switch to task B before it switches. So if you think about temporal difference learning, which other people have talked about, that's not going to work here, because all of that is retrospective. You make an error, then you realize it, then you switch. What we're saying is don't ever do that. Predict what's going to happen next. If you get it right, you never made an error. And prospective risk is the integrated error over all future time. And what you can see is after a few hundred time steps, it never makes another error again. Okay? So this is, in my opinion, the simplest possible failure mode for modern AI, which doesn't include time. This is like the XOR for IID, in my opinion. And what you can see is it's really trivial to fix it. You just add time. Just Just like it was really trivial to fix a perceptron, you just added another layer. We just concatenated another input. So it's very similar in that way from my perspective, and it works really well.
So just, since you began with humans and kind of living beings.
Yeah.
So, like, let me just think about red wine. Like, glass of red wine, good for you, glass of red wine, bad for you. So like this, like government keeps putting out information.
Right.
How do humans deal with kind of like, or political system shifts? Like what would be a natural analog of kind of the minimal, like you're clearly isolating a kind of minimal model where stuff will fail.
Right.
How could I think about this in?
Yeah. So we're designing animal experiments now. But think about like if you're a fox and you want to get a drink from the watering hole, like you don't know when the lion goes there when you're born. It turns out if you go there at noon, the lion eats you, and if you go there at midnight, the lion doesn't eat you. So you can learn that by going close to noon, close to midnight, and you see where the lion is. And eventually, over time, if you in fact learn to not go there when the lion's there, you get not eaten. And if you go there when the lion's there, you do get eaten. So things like that are happening all the time in the real world. For humans, I don't know, I haven't thought through like the real world examples, but there's lots of things in the natural world. There's also lots of things in like our world. Like if you have a pet, and you have a food delivery system on a timer for your pet, you will notice that it will go there before the food comes after a while because it learns the timing, right? So we, meaning animals, learn about time and care about and can deal with it appropriately. And so it really is an input to us in some way that we are learning about. Did you have a question?
Yeah, I did. I was just wondering, like, could you look at analysis of variance as you're moving forward and figure out if there is large difference in variance that might be an indication of some underlying variable that need to be taken into account?
I would think you can use variance. I mean, for us, we just use, the input is literally just x, y pair n times, and that's enough. And the theorem says that that's enough too. So
that would be enough given the structure of the data.
Yeah.
So I'll take this to traffic, for example, where I work. It's if you are learning based on time that there are people being going to peak hour versus non-peak traffic, and you just learn that, you're going to learn not the underlying phenomena, but you're going to learn what is actually manifested by that underlying phenomena. You're going to say, yeah, at 5 I'm going to do this, at 7 I'm going to do this. But if there is a change in the underlying phenomenon, for example, there is a football game that causes people to come out early or later, if you're doing an analysis of variance, you'll be able to discover that.
Right.
Just looking at time might tell you still, given all the data from before, I'm going to stick with 5 anyway.
Well, the result of the theorem is that as long as you include time, no matter what the underlying distribution is, we converge to the Bayes optimal solution. So if the thing that's changing over time is a variance or that's a useful feature, this approach will get it also. But we can talk more. Maybe I'm missing your point a little bit.
I think you're thinking of something with a different distribution than the data, though, no? Like you're saying if the temporal pattern kind of gets shut, if the temporal pattern no longer holds in the training data.
Right.
Okay.
Oh, yeah, okay, I see what you're saying. So all of the theory behind this is that there is one fixed stochastic process governing the evolution of things. If the stochastic process is changing in an unpredictable way, we're screwed.
Okay.
But I think everything is screwed, right? Like the whole field of online learning is basically operating from the assumption that you have no idea what's going to happen in the future. And there's a whole branch of what to do in that situation. And it turns out the optimal thing to do in that situation is just do whatever worked the best in the past. But that's like a very defeatist approach, in my opinion. Like the two extremes are the future is identical to the past in distribution, or we have no idea. We're in this intermediate range of we have some idea, but not a perfect idea. And I think that's a better model of the real world than either extreme. But But if you're in the case where you have no fucking clue about what's going to happen in the future, you can do whatever's worked the best. But then you're not going to leverage the fact that the optimal thing might be a function of time. And so it's a much harder problem in a certain way. Okay, did you have a question?
Yeah, I think you're about to answer, which is these other methods that you're comparing to don't have an explicit knowledge of time. That I guess the question being they fail because they don't have that information and like they don't use it in some way, or that they fail to learn from it.
Yeah, that's right.
I guess that's an or.
Oh, they do not get time as an input.
Okay.
They get the data as an input without time.
Thank you.
Yeah. Okay. The previous figure was like the simplest one-dimensional simulation in the world to illustrate the point where we could prove all the theorems and blah, blah, blah. But you might say, well, come on. What about if it's like slightly more real, like if it's images? Now, obviously, MNIST and CIFAR, two canonical machine learning data sets, are not remotely real. That's complete bullshit to call them real-world data because it's highly contrived. But people do that, and it's certainly more real than this 1D thing that we made up. And the point is, now we don't know what the Bayes optimal is, so I can't prove any theorems about this particular application, but we can still run all the algorithms and show a very similar result, which is like the other algorithms get to chance levels, and we do significantly better than that. And that's true for both CIFAR, which is much more complicated, and MNIST. Yeah, you have a question?
Is there a temporal element to these data sets?
No, so we faked it with time, just the way people do it in the kind of lifelong learning, continual learning in the same fashion, which is we said in both of these cases, there's actually like 10 classes. And what we said is task 1 is classes 0, 1, 2, and 3. Task 2 is classes like 2, 3, 4, and 5. Task 3 is the other ones. And so, and it repeats. So after you get to task 4, then you go back to task 1, then you go back to task 2, you go back to task 3. So it's a similar setup as this, where the tests are switching reliably every some number of samples, but it's switching between classifying, the first 3 digits and then the next ones and the next ones. Okay, yeah, good question. So, well, now you may say, well, that's still pretty easy because now you always know exactly, you can learn exactly which task will happen if you get enough samples. And this, you'll see, this isn't hundreds now, this is thousands and like 10,000. So it's harder to learn, but you can really perfectly predict exactly which task is going to come if you learn that. So let's make it slightly more complicated. Now there's 4 tasks. Here's the simulated version. And the 4 tasks is not going to be deterministic which task comes next. It's probabilistic, governed by a non-Markov chain. So what's happening is it switches between task 1 and 2 using Markov dynamics. So with high probability it stays, but with some probability it switches to the other task. But then every 10 steps it switches to a different Markov chain, going to 3 to 4. So this is non-Markov. So if you're using like an HMM or a Kalman filter, things like that, it's not going to work. And you don't know exactly which task you're going to be at any given time. And here, what I'm just showing is the 4 tests. So it's really simple. Task 1, you're red if you're in this quadrant, and you're blue in this quadrant. Task 2, it's like this. Task 3 is this, and task 4 is this. And there's one of the key parts of designing this is that which quadrant you're in, you have to also know which task you're in, because it changes. Like in task 1, this quadrant is red, but task 3, this quadrant is blue. So there's no fixed hypothesis that works for all tests. You really have to change when the task changes to do well in this task. Yeah.
When you switch, is it random which one you start at, or?
Yeah, oh, you mean between these?
Yeah, when you switch.
Yeah, there's the prior is I forgot what it is, but something. Yeah. Okay, and so the results are the same. Like, in this really simple version where we can prove things, what Bayes optimal is because we can derive it, the prospective learning can eventually, after a few thousand steps, converges to the Bayes optimal thing. And the other things converge to something, but they're not doing very well. We did a version of it with MNIST and a version of it with CIFAR with a similar deal, 4 tests, switching, but not, according to those same non-Markovian dynamics. And Other algorithms are getting like, about chance again, and we're getting substantially better. Again, it's hard. It's like thousands or tens of thousands of steps, but we're converging to something that seems like maybe optimal. Okay? Well, for any of you who have noticed that there's something called ChatGPT and these other things now, you may think, seems like they might be doing perspection, right? Like, you give it a bunch of words and you ask it to say, what's the next 100 words or whatever, and it can do it. So we thought, okay, yeah, maybe LLMs can perspect. Clearly, these other algorithms that we built do not, but maybe LLMs can do it. So here's what we did. We tried with a bunch of LLMs. This was like maybe 6 months ago, so they're slightly outdated now, but we used some version of Llama and Gemma, and we gave it prompts like this. And we tried a bunch of other prompts, but this prompt was, consider the following sequence of outcomes generated by two Bernoulli distributions where all even outcomes are generated by a Bernoulli distribution with parameter p, and odd outcomes are generated with a Bernoulli distribution parameter 1 minus p. So exactly the same as the simulation we started with first. Even simpler, because it's an unsupervised problem. You're just trying to estimate p. And so we give it this. This is the data, and this is a prompt. And then we ask it to generate the 20 most likely sequences of outcomes. And then we look at the statistics of how well it performs. And if it could do perspection, then you would see over time it gets good. We gave that sequence of the first 20 steps to our algorithms, and it very quickly converges to never making another mistake again. But Llama 7b and Gemma 7b are both doing really crappy. So they're not perspecting at all. They're not learning anything as far as we can tell. So we wondered, that's weird. Like, this is not very hard. You kind of just have to flip a coin a bunch of times. What's going on? Okay, I don't have this slide here, but it turns out we just asked it then, flip a coin 10 times, but have the probability that it lands on heads be, say, 20%. And they can't do it at all. They flip it so it lands on heads about 50% sometimes 0%, sometimes 100%. They're all over the place. It was true for Llama and Gemma. The other ones, like if you use more recent versions of ChatGPT, it'll actually write Python code to get the answer right. Or you can at least prompt it to do that. And then those ones will get it right. But they have to use the code. And the point is like, this is the simplest inference imaginable, basically, like just sampling a coin flip that's biased. And they are much worse than humans at it. Like humans can do this approximately okay, and we haven't quantified it very carefully, but like they're really, really bad at the simplest inference possible. So if anyone thinks LLMs can do inference or think or reason or do causal inference or have sparks of AGI, you can tell them I said that's utter nonsense. They can't flip a coin. If you can't flip a coin, you can't do any of the other things. Anyway, we can fight about that later. I'm sure lots of you want to. Yeah.
Is the P.9
yeah,
90% bias coin? Or?
Yeah, though 90% of the time it lands on heads. Yeah, and it's, they're all over the place. Okay.
So this may be a little bit of a technical question. How do I actually set this up with an LLM? Like, how do I...
Set prompt.
Oh, we just put in... Oh, that's it?
Yep. I mean, we tried lots of other prompts, but none of them worked. And I guess I should say a caveat that we make clear in the paper that I haven't made clear here is, like, maybe we're prompting poorly. Maybe you can figure out a better prompt. And, like, our bias wasn't to find a good prompt, just being totally transparent with you. So, like, if you worked really, really hard,
in terms of, like, if I view... So, I mean, the test I would like is somehow just a language test where, you're kind of feeding in words, like, do the same test, but with words rather than numbers. Because the training corpus is all words.
Right. Well,
I think they do better with words than with...
We played with, like, putting spaces between the numbers and commas between the numbers. So, like, because I was worried they were tokenizing this weirdly, it didn't help. We could maybe replace zeros and ones with, like, heads and tails, but I don't think it's going to work. They don't do the things that people think. They predict the next token. and they've never seen sentences like this before. So they're just not in the training data. So they're going to suck at it, I think. Yeah.
Yeah, I was just gonna ask, like, have you tried what they call chain of thought? Like, just showing them how to do it first,
No.
and then, because I think that, I mean, I obviously agree with this. I mean, they're not gonna be able to do it.
Right.
But I think, especially with like the current models, if we were to show them like one shot, maybe a couple, even with one shot of an example of how to do it, and then they can actually start doing it.
Well, look,
with some stuff.
Let's try together on Sonnet or 4.0 right after and see. Like, who knows? There might be a way to prompt them to get it to do it. The point is, it's not that trivial to get them to do it because I tried a bunch of prompts and a bunch of them and it didn't work. I think that's as strong a claim as I can make. Trivial, obvious prompts didn't work. And with a variety of different tokenization strategies too. Okay, so everything I've said so far, there was no action. It was all inference, right? You just guess what's next. If you're right, nothing about the world changes, nothing about you changes, you just get some reward. So that's actually a very simple kind of statistical problem. And we're interested in taking actions. I mean, LLMs aren't, they don't act, but we as conscious agents are. So the next question we had is, can we deal with prospectively learning in such scenarios? And I just want to say this is very preliminary work. Like, our NERVs paper ended with the last slide. This is all from the last month or so. But I thought it's cool and I wanted to tell you about it. So we designed this problem called prospective foraging. So if any of you know foraging, I'll tell you how it's different. If you don't know foraging, just know that what people used to call in anthropology hunter-gatherer societies, they now call foraging societies. It's like the main thing almost all mobile agents do all the time. And foraging is defined somewhat formally as a sequential search for general resources. So the deal is, I want food. I don't want this particular apple, just any food. And I'm going to walk around the world sequentially making decisions. Do I want to exploit this resource now or keep going and look for something else? And what's interesting about it is if I choose to not exploit it in normal foraging, it just stays there forever. Okay, that's in foraging theory. However, in the setting that we've set up, it doesn't stay there forever. And I claim this is much more realistic because if you've ever, say, been a squirrel looking for nuts, you might notice that if you don't get that nut, a different squirrel gets it, or it rots, or like an owl gets it, or whatever else eats nuts. I don't know. So here's how we set this up. We use OpenAI's GIM, Frozen Lake, a very simple scenario. There's 7 possible patches. And on this one, which we'll call A, and this one we call B, there's resources sometimes. And so here's how it works. This x-axis is time, showing the reward. Basically, at time 0, A has reward, but it's decaying over time until it gets to 10 time steps and there's nothing there. However, at time 10, reward shows up at B, and it starts decaying until time 20. At which time the reward shows up at A again. Okay? So the obvious optimal thing to do, obvious maybe not the right word, but the provably optimal thing to do in this setting is hang out at A until about here. If it takes 5 steps to get to B, leave it here so that you get to B right here. Because this is when B is maximal resources. Then you hang out at B till here, and then you leave till you get back to A. You always want to be at the resource when it's at the location when its resource is maximized. So this is different, as I said, from the way people normally study foraging because the resources aren't changing unless you're there, in which case they get depleted. But our claim is they're getting depleted whether you're there or not. And we can change it so it gets depleted faster when you're there, but it won't really change the main results. Okay, so does everyone understand the setup? Okay, so as I said, optimal foraging theory, there's a fundamental theorem, marginal value theorem, which says you leave a patch when the average resources everywhere in the environment is higher than your current patch. So in optimal foraging theory, what you should do is leave the patch A at this time, which means you get to B here. And then you get to A here. So you get almost nothing. It's really bad. I mean, it's optimal if you make a totally wrong assumption about nothing ever changing. But this whole talk is about things are changing in time, whether you do something or not. And so optimal foraging theory leads you to the totally suboptimal behavior. And there is an optimal thing to do, which is really straightforward, and we can prove exactly that you should always leave however many time steps it takes to get to the optimal thing before it switches. Okay, so, and people have used reinforcement learning to solve foraging problems recently. So we took whatever the state-of-the-art reinforcement learning algorithms were that people have used for foraging problems. There's a couple of NeurIPS papers in the last few years on this. And the best thing that people have done is something called the advantage actor-critic reinforcement learning algorithms. And what I want to point out is reinforcement learning algorithms are designed to have multiple episodes. Right? So you play, say, a game of chess. At the end of it, you see whether you won or lost. If you won, you get a reward. If not, you don't, and then you play again. And once you play like 1 billion times, you learn how to do it. So we changed this thing to be able to be amenable to reinforcement learning by saying, you can't just run back and forth forever, but you have like 100 time steps. And then you reset and you do it again. So now you're going to have like many, many episodes. And so what I'm showing here is performance as a function of the number of episodes for many runs of the algorithms that people use for foraging. And what you can see is this is the optimal performance, and none of the runs can reliably get there. But some of the runs, sometimes they do get pretty good. And this is just showing the cumulative reward over time. The blue line is the optimal. The red line is optimal foraging theory, what it says you should do. And they're doing pretty good in this setting where we changed it. But now we take the episodes away. Right? So now there's only one long episode, which is a lot more like life. Like, we don't really get retries. We just have one long life. I mean, maybe if you believe in reincarnation, but just for this life, we don't get retries anyway. And we run the same algorithms, and they learn to do chance levels. They're really not learning anything. And here's the performance. They're not getting this red line is marginal value theorem. Here's optimal. What you can see is they are learning, but like they're learning worse than, well, they get the chance performance. So they really can't do it. Now, what I would love is for the next slide to be like, and look, prospective foraging solves it, but like I don't have that result yet. So I don't know. But what I can tell you is whatever they're doing, the thing that people have used to solve foraging does not seem to work at all for this problem. Yeah?
When you say single episode, so with these methods, you're initializing a policy, single episode runs, where is the learning or reward happening?
There's like a few papers in RL where the way you do it is like you look at the last, say, 100 steps and you update the parameters based on that.
Okay, so they're learning, so they're not, in the multi-episode case, they were updating at the end of an episode. Here, you're doing some kind of online learning.
Yeah, so like if in the multi-episode thing, each episode was 100 steps, what we did here is after 100 steps, you update the parameters again. So that's why I wrote reset free. People call it sometimes reset free because you're just not resetting to go back to the initial position ever. Other people have called it single episode or single life learning. And I just also want to say, like, all this reinforcement learning is very new to me. Reset-free learning is extremely new, I think, to everyone. I'm not an expert in it, so like it could be similar to the LLMs. Like we just didn't do it good yet. But we literally took the algorithms from the most recent papers and ran them. So they seem to run like. What I can say is the algorithms that we ran solve the problems when we run them on when they say they should solve them. But on this problem, they don't at all. So I feel confident that those algorithms don't work. Okay. I want to talk about real-world data, but I don't have time, and the results aren't cool yet. So I'll just say we'll talk about that next time. So we want new models of learning. We, meaning me, my lab. We're working on one called prospective learning. It's a model. And as you know, all models are wrong. Some are useful. I actually think a better phrase would be all models are wrong. Some are useful along certain dimensions, and others are useful along other dimensions, but different amounts. So we think prospective learning comes closer to describing what's happening biologically and solves some real-world problems in AI. However, we need a lot more work. Our algorithms, they're basically on toy problems, so we need to make them work at scale. in terms of control, like we don't know how to do it yet for optimal foraging, and we don't have any interesting real-world examples yet. All of these things are being worked on by different students in the lab, and because it's so new and I don't really know what's going on, we're super excited about collaborations. So if you know anything relevant, and I think all of you here do, like, and it's interesting to you, it would be great to talk more and figure out how to collaborate. There's a bunch of papers we wrote on this, but the most recent relevant one is this, Prospective Learning, Learning for a Dynamic Future, which we're presenting at NeurIPS like in 2 weeks. And most of the work was done by Ashwin in the lab, but also all these other people helped. And I'm particularly grateful to my wife, who let me hang out in California for a few days while taking care of our 3 beautiful children, including taking them to school every day and putting them to sleep every night and dealing with them when they wake up in the middle of the night while I'm just chilling, hanging out with you guys. So thank you, and I'm happy to take any questions.